But tomorrow, talk about something else. Okay, with the dot product, what do we know so far? We know that A dot B is the norm of A times the norm of B times the cosine of theta. We also know, because of this, that the cosine of theta would be equal to A dot B over the norm of A divided by the norm of B. And that's sort of a handy thing. What does that tell us? It tells us that we could find the angle between any two vectors. And I just say that, some of you might think, oh, it's not such a big deal, or whatever. But it's sort of a strange concept to think about the angle between vectors when you think about the fact a vector can be placed anywhere on the plane. So for example, I could say, all right, here's a vector A over here, and here's a vector B over here. And if you look at this calculation and you did the work for it, you would get the angle between vector A and vector B. So this formula is saying about where the vectors are placed on the plane, but it still sort of says, hey, look, there's an angle between these things. In terms of visualizing that angle, I guess the most natural thing is to pick this vector up and move it over here so that they're tail to tail, and then the angle theta is the angle that would be in between them when they're placed that way. Okay? All right, so that was sort of fun stuff. You're able to take two vectors, find the angle between them. We also know now that if we said this, if vector A is perpendicular to vector B, then A dot B is equal to 0. All right, and that's easy to see why if you look at the dot product in this definition up top here, right? If the two vectors are perpendicular, then the cosine of the angle between them would have to be cosine of pi over 2, right? That would be equal to 0, and your dot product comes back at 0. Okay. Turns out the converse of that statement is also true. So if A dot B equals 0, then vector A is perpendicular to vector B. Okay? So it's important when you write down if-then statements, you should always ask yourself, is the converse true? Can I use this relationship in reverse, so to speak? All right. So let's draw an x, y, z axis. Okay? And what I'm going to do is I'm going to put a vector on here. I'm going to put this vector. The vector is going to be, we'll call it vector v, and it looks like this. It is, okay, 0, 2, 2. Those are its components. This happens to be a position vector because I placed it in such a way that its tail is at the origin. And that means that the head of this vector is pointing to a point in 3 space whose coordinates are the same as the components of the vector. Sounds like a lot to say, but we have to be formal with that language. Okay, so the first question I want to ask is, what angle does V make with the x-axis? So pause for a minute and think about that. So pi over 2 radians. Sort of tough to draw this. What I'm trying to say here is, what's that angle? The angle sort of sweeping back to the x-axis, right? You have to imagine that, and so forth. And we know it's going to be perpendicular to any vector that lied along the x-axis. How do you know that? Well, you picked any vector that lied along the x-axis, right? So let's just make a note of this, right? So any vector, I should say parallel to the x-axis. Oh, that's weird. Sorry. That's weird. Parallel to the x-axis. Okay. If you want, you might as well, what's an easy one? Just choose I. It's not a bad idea. Okay, and if you do that, that vector has components 1, 0, 0. Okay. Well, we know, because of what we just said a moment ago, if we take vector v and we dot it with I, what are we going to get? We're going to have the vector 0, 2, 2, dot 0, 1, 0, 0, and that's just going to be 0. So that means that these things really are perpendicular. Okay? All right, so 2 more questions. What angle does vector v make with the y-axis? And what angle does vector v make with the z-axis? So I'm interested in now this angle and this angle. Okay? So let's give those things names, actually. This angle here, the angle between the vector v and the z-axis, I'm going to call that. Okay? Call that gamma. And then we'll call this one over here, between the vector v and the y-axis, beta. Okay. So the question is, what's the angle between the y-axis and the vector v? And what I'm going to do is I'm going to go back to my dot product definition that we said earlier. The cosine of theta could be a dot b over the norm of a times the norm of b. Well, I need a vector in the direction of the y-axis. So that's correct. Yeah, it makes sense to pick the j vector in that case. So that's what we're going to do. We're going to find the angle between v and j. So I'm going to write that this way. Cosine theta equals vector v dot j. There we go. That's weird. Is my j? I don't know. I just made a mistake there. I wrote my j backwards. I'm a little tired today. Norm v, norm j. So if you just think ahead a little bit, you might think you know the answer to this right away. I mean, if you look at the vector v, it goes over an equal amount that it goes up. So you would expect beta to come back as pi over 4. So I wrote theta here. Let me be more careful. Let's say beta to be consistent with how I labeled the picture. Okay. Vector v has components. Here we go. Ready? 0, 2, 2. And the vector j has components 1, 0, 0. Now on the bottom, we're going to do the norms of these things. Well, the norm of vector v would be the square of all these components added together. Okay, yes. And I made a mistake again here. 0, 1, 0. Is that better? We'll just have to redo this later. Okay, vector v then has a norm of 0 squared plus 2 squared plus 3 squared square root. It's going to be the square root of 8, I guess. Right? Multiplied by the length of that vector, which is just 1. Okay. So we're expecting to somehow figure out that beta is going to be pi over 4. We suspect that, and sure enough, it will happen. The dot product on top, right, is 2. And on the bottom, we really have 2 rad 2. Well, that's 1 over rad 2. Some of you might think of that as rad 2 over 2. But now we're saying, hey, what's an angle whose cosine is square root 2 over 2? That means that the angle beta must have been pi over 4. Okay, so now we know that angle. And I'll tell you now that a similar calculation, you'll figure out that gamma is also pi over 4. Just to be precise, we should, just in case anyone's wondering, we should say that when I ask for the angle between a vector v and the z-axis, I'm really asking for the smallest angle between the vector and the z-axis. So we don't have anything where we're cycling back and getting reflex angles or anything strange. Or some people might say, hey, wait, the z-axis extends down here. How do I know you're not asking for maybe that angle, right? that angle would be pi minus gamma. Okay? So we're going to say that these angles are the smallest angles between the vector and the axis. Okay. So if you think about it, we could sort of come up with like a quick formula for all these angles. All right? So just so we're clear on our picture here, this first angle I asked about at the beginning of all this, what was the angle between v and the x-axis, we kind of knew by inspection that that should come back as pi over 2. I'm calling that angle theta. Okay? I'm calling the angle between the y-axis and v beta, and between the z-axis and v gamma. So we can actually write some things down here. So for example, the cosine of theta would just be v dot I over norm v. And now I could write norm I, but I don't need to, right? The norm of I is 1. So we could just leave it like that. The cosine of beta, we just showed, was v dot j over the norm of v. And for the same reason, we're not going to write norm j, because norm j is 1 also. And then lastly, cosine gamma is going to be v dot k over the norm of v. Okay? These three things together are referred to as the direction cosines. Okay? So this dot product gives us a quick way to find the angle between any vector and any of the three axes. Okay, so here's a fun thing to think about, right? Let's just say this. Let's say let vector v equal v1, v2, v3. So they're the components of vector v. And then these things simplify a little bit, don't they, right? Because we know that v dot I, right, I has components of 0 in the y direction, 0 in the z direction. So when I do v dot I get just the x direction of v, or v1 over norm v. That's even nicer, isn't it? Right? And then by the same reasoning, vector j has 0, 1, 0 as components. So when I dot it with v, I just get the second component of v. And the same reasoning here. Okay. That's kind of nice. So let's seemingly switch gears for a minute, but maybe not. Okay? All right, so let's just go back to like physics for a minute here. And if we're looking at a vector that's in the 2D plane for a minute, we'll call this vector v. In physics, you got very good at saying, hey, wait a minute. If we know this angle theta above the horizontal, then we have the ability to find the components of v. Like this is v sub x, right? And then in the y direction, there's v sub y, and that's usually the notation you used. Here's a copy of v sub y over here. And you know how to find these things, right? Okay. Sort of a fun thing, if you think about what we talked about with vector addition for a minute, it's clear here that v sub x plus v sub y equals v. Right? If you add the vector v plus the vector y, you'd get the vector v. Right? And we took advantage of that head-to-tail sum procedure for vectors to get some very fun parameterizations a while back, if you remember correctly. Okay, so now the question I'm going to ask is this, right? If you think about it, just before I ask that question, if you think about it, here's the vector v. It has a component that moves in the x direction, right? Now, if you want to think temporarily of vector v as like casting a shadow, vector v sort of casts a shadow onto the x-axis if the light is coming from up here, directly above. So let's pretend we have all our rays of light pointing down like this. These are not vectors. It's just light coming down. If you did that, vector v would cast a shadow onto the x-axis that'd be exactly v sub x. Okay? That has a fancy name. That's sometimes called the projection of vector v onto the x-axis. Okay? So we can generalize this idea. It turns out that you can always take a vector and say, what's its projection or its shadow onto another vector? Okay? So let's go to a new page here. And let's consider two vectors. So let's consider this picture. This is going to be vector A, and I have some vector B up here. Okay. And I might ask you, hey, what can we say about the shadow of vector B onto vector A? Put another way, what I'm really saying is, there are two components of vector B relative to vector A. In other words, let's say the following. Okay. Okay. So what we're going to do is we're going to sort of consider like the same case. We're going to imagine like light shining down on this thing, and it's shining down, but in such a way that these rays of light are perpendicular to the vector A. And if you do that, then B would cast a shadow onto A that looks like this. There it is. Okay. Now, it doesn't make sense to call this blue vector B sub x. We wouldn't call it that. Okay. We'll get a name for it shortly, but let's start by just saying this. I think if we want, we can get the magnitude of this. In other words, how long is this vector? That's the question I want to ask. All right, so in order to do that, you need little information. Let's pretend the angle between the vectors is theta. The length of that vector would be, now let's just be careful. I mean, we've got to be precise with our language. I would say B cosine theta, and that would be a reasonable thing to think right away. But remember, B stands for the vector B. And I think we want the length of B, which we would denote as norm B, or absolute value. That's right. So there you go. That's what we have. All right. So how could we do that? Well, we can get the norm of B. We can find the angle between the vectors and do our thing. So let's just. So what do we also know? So we also know the following. We know that A dot B is norm A, norm B, cosine theta. Keep in mind, these are scalar quantities, right? A dot B is a number, norm A, norm B are numbers, and cosine theta is a number. So we're not going to yield any vectors here. But if you look at it, here's the thing we really want to solve for. That is the component of B along A, right? So we can get that alone. We could say norm B cosine theta is A dot B over norm A. All right. I'm just going to do one extra thing. I'm going to write this in a slightly different way. I'm going to write this as A over norm of A dot B. And you should take a look at that expression for a minute and convince yourself it makes sense to have a dot product between them. All right? When I write a dot product on a paper, it only makes sense to do a dot product between vectors. So you should ask yourself, are these things vectors? And they are. B is clearly a vector. That's a vector. And then this is actually a vector also. But it's a special one. Question is, what's special this vector? Question is, how long is this vector? Okay. In order to see that, it might be worth just making a quick example and see what happens. So let's pretend for a minute that vector A had some components. Let's pretend it had components 1, 2, 3. Right? Let's consider what the vector norm A looks like. Oh, I'm sorry, not the vector A over norm A looks like. Well, the norm of A would be the square root of 1 squared plus 2 squared plus 3 squared. I think that's the square root of 14. Okay, so this vector is 1 over rad 14, comma 2 over rad 14, comma 3 over rad 14. Right? And what's that about? Well, find the length of this thing. Find the length of A over norm A. And surprise, surprise, what do you get? You get 1 over 14 plus 4 over 14 plus 9 over 14 square root. That's the square root of 1, which is 1. So it turns out the answer to our question is that vector has a length of 1. That means it's a unit vector. Okay? You can give that some thought as to what that means. It's sort of interesting as to what's happening there. So one final statement to make. If you think about this quantity here that's in the green box, it's equal to A dot B over the norm of A. And we know that A dot B yields a scalar, and norm A is a scalar. So when we're all said and done, this is a scalar. And I'm not surprised by that at all, because we were asking originally how long is the vector right here, this vector that is sort of like the component of B, I guess we'll call this is what it's sometimes called, it's called the component of B along A. And so far we've found that the length of that could be expressed by this expression, A dot B over the norm of A. All right, so what we'll do next time is we'll take this thing that we have the length of now and turn it into a vector quantity, right? And I actually know how long this vector is, but then the question is, what is that actual vector? And it turns out we can define that in terms of vector B and vector A as well.